It's just so nice coming and meeting everybody and making connections with people and actually having a sit-down conversation with them, getting contact information and just kind of being seeped in the environment of a bunch of really intelligent, really driven developers. I mean, it's awesome.
Before we get going, a quick warning. When the Back to Basics topics were doled out this year, I drew the short straw. There is way more useful information about generic programming in C++ than I could possibly present in just 1 hour or even in 1 day. I have the unenviable task of deciding what information is most useful and presenting it in a way that doesn't leave you feeling like you are drowning in information or trying to drink from a fire hose or like everything is going by at race car speeds. If you feel like you can't absorb everything I am throwing at you, don't panic. You can always watch this talk again and again on YouTube until it all sinks in. I am David Olsen, a compiler engineer at NVIDIA. I will do my best to give you an introduction to generic programming in C++. The word generic, in general, refers to something that works in a wide variety of situations, or to something that is not specialized for any particular purpose. A generic hotel has clean, comfortable rooms with 1 or 2 beds, a large TV, and a small desk. The hotel will likely serve breakfast and may have a pool or a small gym, but it doesn't have much else. Generic hotels are useful to a wide variety of travelers, such as business travelers attending a conference, families on vacation, or people on road trips who need a place to sleep for just 1 night. It may not be the ideal place for anyone, but a generic hotel is a suitable place to stay for almost everyone when they are away from home. A generic suburb in the United States has detached single-family homes, often close together, usually with 2-car garages, in residential neighborhoods with lots of cul-de-sacs. A generic suburb is almost nobody's dream home, but such suburbs have spread throughout the country because they are suitable homes with the right combination of affordability and comfort for many people. But what do we mean by generic programming? It means writing code that works in a wide variety of situations. In practical terms, that means writing code that works across a variety of different types, especially types that are not directly related. For example, we can write generic code that adds up the values in a container. For this to work, our language needs to give us a way to specify that the types T and C are just placeholders for actual types that support, among other things, operator plus equals for type T and the range-based for loop protocol for type C. Generic programming is the ability to write this code just once and have it apply to any types that meet the necessary requirements, rather than having to repeat this same code pattern for all value types and container types for which we want to compute a sum. Generic programming is a form of static polymorphism, which means that the polymorphism, or the ability to work with different kinds of things, happens at compile time. Generic programming happens in statically typed languages. Even though the generic code has placeholders for types and maybe for some other values, the compiler resolves all of those at compile time. The compiler figures out all the actual types that will be used by the generic code. So there are no runtime type checks needed and no runtime failures about an object of an incorrect type. Generic code is often not the ideal code for every situation. We could probably shave a few nanoseconds off the execution time or come up with an API that better fits our use case if we wrote custom code for our particular situation. But using generic code is usually the most practical approach because the generic code is more likely to be correct because the development costs are less. Generic code is suitable for most situations, like generic hotels and generic suburbs. In many programming languages, generic programming is referred to as generics. C++ is unusual in that it refers to generic programming as templates. This talk is almost entirely about C++ templates. I would have liked to cover more ways of doing generic programming in C++, but a proper introduction to templates would take many hours. So all the template-related material crowded out everything else that I wanted to talk about, such as reflection, which is a very different form of generic programming that doesn't use templates at all. I want to avoid discussing template metaprogramming and focus on the basics of templates, but a little bit of metaprogramming will creep in here. The basic template definition is the keyword template followed by a comma-separated list of template parameters enclosed in angle brackets. After that is what mostly looks like a normal declaration. The thing being declared via class, struct, function, type, alias, variable, or concept. The most common template parameter, I'll cover the less common ones later, is the keyword class or type name, followed by the name of the parameter, maybe followed by the default value. A template should almost always be defined in a header file, not in a CPP file. This includes template functions. Regular functions are normally declared in header and defined in a CPP file. But for a template to be used, the compiler needs to have already seen the full definition of the template. You won't run into the problem of multiply defined symbols. The same template is used in multiple source files. Compiler will take care of that automatically, usually through the magic of weak symbols. Just define all your templates in a header file. Don't think about it. Here's an example of a class template. In this case, a very simple class that holds two values. Starts with the template keyword, followed by the definition of the template parameters. In this case, there are two parameters named t and u, which are types. We'll see how that works later. The thing being declared is the class template pair. Within the definition of class template pair, the template parameters t and u can be used just like any other type, such as types of data members, the types of function parameters, and the return types of member functions. When defining template parameters, keywords class and type name are interchangeable. The definition of pair, this definition of pair is identical to the previous one. It is for historical reasons, which I won't try to explain, that two different keywords can be used for the same purpose. I use class in all of the examples in this presentation. Many coding guidelines specify the use of type name instead. Get used to using either keyword, both when reading code and writing code. Follow whatever convention is used in the code base that you're working with. Now for example of a function template. Again, the definition starts with the template keyword and template parameters. There's only one parameter named t, which is a type. In the function signature and the function body, we can use t just like any other type. In this case, as part of the type of the function parameters and as the type of the local variable. Here we have two examples of the type alias templates. The first one just yields a pointer to the given type. It's really simple and kind of pointless, but it should be easy enough to understand. The second one shows how type aliases can save a lot of typing and give a name to an abstraction. This is getting into the realm of template metaprogramming, which I want to avoid. This is really a template meta function that works on types. Such things are very useful, way beyond beginner material. Here is a variable template. It looks a lot like a regular variable definition, except that it has template parameters that can be used in the initial value of the variable. Now let's talk more about template parameters. There are three kinds of template parameters. So far, all of the examples have been of the first kind, type template. A type template parameter represents a type. The argument for the parameter can be any type that the C++ type system can represent. A type template parameter is defined, as mentioned earlier, the class or type name keyword followed by an identifier. A non-type template parameter, sometimes abbreviated in writing as TTP, represents a compile time value of a given type. Because generic programming in C++ is entirely a compile time construct, the value that is bound to a template parameter must be known at compile time. Runtime values are not supported. There are restrictions on what type a non-type template parameter can be, which are too complicated to explain in detail. Essentially, the compiler must be able to create values and compare values for equality all at compile time. That means integral types and enums are always a suitable type, and that's what most people use for non-type template parameters. Since C++20, the type can be specified as just auto, in which case the compiler will deduce the type from the type of the template argument. Don't write code with auto non-type template parameters until you are proficient with templates. I mention it here only so you might have some clue what they are when you encounter one. The third kind of template parameter is a template parameter. As its name implies, it represents a template. The template parameters of the template parameter need to be specified. This gets recursive, with template parameters defined within the definition of a template parameter. It's all very confusing. Template parameters are best understood by playing around with them. The Compiler Explorer link at the bottom of this slide may be a good place to start. It has examples of all possible kinds of template parameters. For all the template parameters, the name is optional. It's legal for a template parameter definition to be just the keyword class and nothing else. If the parameter doesn't have a name, then you can't refer to it from within the template definition, but there are times when you don't need to. But there are no definitions where a template parameter cannot have a name, so it's fine to always name your template parameters. All three kinds of template parameters can have a default value, which is the value that the parameter is given if no template argument is supplied. A template parameter without a name can still have a default value, which happens in the wild more often than you might think. And finally, template parameters can be variadic, which means a single template parameter can match a list of any number of arguments. A variadic template parameter is defined by putting an ellipsis just before the name, or just before where the name would be if there was one. Variadic parameters cannot have default values. Variadic templates are important, but I just couldn't find the time to fit them into this presentation. This is unfortunately the only mention of them. An example of a non-type template parameter is the standard library class std_array. It has one type template parameter, which is the type of the elements in the array. And it has one non-type template parameter of type size t, which is the number of elements in the array. Since non-type template parameters are compile time values, the parameter n can be used in places where a compile time value is required, such as an array bound or the return value of a const expr function. Class templates can, of course, have member functions. Those member functions can even be function templates themselves. It takes some getting used to, having a template nested within a template, each with their own template parameter list, but it is quite common and very useful. But the purpose of this slide is to encourage you to always define member functions of class templates within the class, as shown here. It is possible to define the member functions outside the class, as shown on this slide. But getting the syntax correct is challenging, since all templates, including member functions of class templates, should be defined in header files. There is no good reason why a member function needs to be defined outside of its class. So do the easy thing and define member functions inline. To use a template, the template name is followed by the template arguments enclosed in angle brackets. The template arguments are the values that each of the template parameters should have. The number of template arguments should match the number of template parameters, or at least the number of parameters that don't have default values or can't be deduced. And the kind of each template argument must match the kind of the template parameter. For a type template parameter, the argument must be a type. For a non-type template parameter, the argument must be a compile time constant of the correct type. For a template parameter, the argument must be the plain name of a template without any template arguments. Here's an example of using the class template, function template, type alias template, and variable template that we defined earlier. The templates only have type template parameters, so the template arguments are all types. Sometimes the template arguments don't need to be specified, even if there are no default values for the template parameters, because the compiler can deduce the values of the template arguments. In this case, we don't need the template arguments for the class template pair or the function template swap pointed to. So we can leave them out entirely, and the code behaves the same as if they were there. I've given you the very basics of generic programming, but not enough to be actually useful. Now I will cover a variety of other topics that are important to know and give more examples of and advice for using and writing templates. The next important concepts are substitution and instantiation. These terms are often used incorrectly. When you hear someone else use one of these terms, consider the possibility that they really mean the other one. While it would be good if you learned to use these two terms correctly, it is more critical that you understand the concepts behind them and know what the compiler is doing when. Substitution is the simpler operation, and it's the first thing that happens when using a template. The compiler evaluates the template arguments, whether they are explicitly specified, the default values, or deduced, and substitutes the value of the template argument for the template parameter. That's it. The compiler doesn't look at or check the definition of the template, only the declaration and its template parameters. The result of substitution is an incomplete class or a function declaration. When instantiation needs to happen, it happens after substitution. It's the more involved operation. Once the substitution of the template arguments for the template parameters has happened, the compiler then checks the definition of the template, such as the class definition or the function body, to verify that the values of the template arguments are compatible with how the corresponding template parameters are used within the definition. The result of instantiation is a fully defined class type, or function, or type alias, or variable. Let's look specifically at substitution of class templates. Usually, substitution of a class template is followed by instantiation. But there are at least two situations that I can think of where substitution happens without instantiation. One, when an incomplete type is all that's needed. And two, when doing class template partial specialization resolution. Ignore the second case for now. For the first case, the most common situation in which only an incomplete class is needed is when the code only uses a pointer to the type and never dereferences that pointer. Substitution for function templates is different enough from class templates in the details that it's worth discussing it separately. Substitution of function templates happens during overload resolution. When resolving a function call, the compiler does substitution on all function templates that were found by name lookup, including argument-dependent lookup. Substitution results in a function declaration only. The compiler does not check the function body or create a full function definition. But creating a declaration means that the compiler checks the entire function's signature, including, among other things, checking that the parameter types, the return type, and the no except clause are all valid. Once substitution is done, the compiler takes all the declarations of the substituted function templates and declarations of the non-template functions and completes the overload resolution. Only the function that is chosen, the one that is the best match among all the candidates, is then instantiated. All the function template substitutions that were not the best match are ignored and are not instantiated. Now let's look at instantiation of class templates in more detail. When a class template is instantiated, which remember happens after substitution, the uses of the template parameters within the class are effectively replaced by the corresponding template arguments, and the class definition is again checked for correctness. I'll have an example of this on the next few slides. When instantiation is complete, the result is a complete class type that can be used like any other class type. One important thing to note, member functions of class templates are not instantiated when the class template is instantiated. The member function, even if it is not a function template, is treated like a function template and is instantiated only when it is called. To refresh your memory, here is the class template pair that was an example near the beginning. If we write pair of int comma data in the code, where data is some user-defined type, in a context that requires a complete class definition, then the compiler will behave as if this was in the source code. Note that all the occurrences of t and u in the class definition have been replaced by int and data. The member functions are declarations only because the member functions of class templates are not instantiated until they are used. The funny identifier here represents the compiler's internal name for the instantiated type. In this example, instantiation went smoothly. Now let's look at an example where it doesn't. If we instantiate the class template the same way, except that the first argument is an array of 10 ints rather than just an int, then the compiler will behave as if this were in the source code. The data member is fine. M0 can be an array of 10 ints. The parameter is fine because, for obscure historical reasons, parameters with array types are automatically converted into pointers. But this is a problem. It's a function returning an array, which is not allowed, even as just a function declaration. This causes instantiation to fail because the class definition that results from replacing the template parameters with the values of the template arguments is not a valid class definition. An instantiation failure is a compilation error, with the compiler doing a decent job of explaining what went wrong. Now for function template instantiation. This happens when a function template is called after making it through overload resolution. The process is similar to instantiation of class templates. Replace the use of template parameters within the function body with the corresponding value of the template arguments. The result is a complete function definition. A quick example, this is the swap pointed to function template from before. If the compiler needs to instantiate the function template with the template argument double, then it will produce something like this, with all the uses of t replaced by double in the signature and the body. This is a very important slide, so please pay attention. In the previous slides, I showed an example of a failure during instantiation being reported as a compiler error, but I didn't show a similar example for substitution because substitution failure is not an error. This is abbreviated SFINE. I've heard the acronym pronounced several different ways, but SFINE is the most common. When substitution fails for whatever reason, the compiler does not report an error, at least not right away. Instead, the template entity where the substitution was happening is ignored or discarded. When substitution fails during overload resolution, that function is no longer considered a viable function, and it is removed from the overload set. Substitution failure can lead to an error in some cases. For example, if all the functions in an overload set have a substitution failure, then the overload set is empty, and the compiler will report an error about an unresolved function call. The error is an indirect result of the substitution failures. It is not an error about the substitution failure itself. If SFINAE were not a thing, if substitution failures were an immediate error, then overloading of function templates would not be feasible. And class template partial specialization would not be feasible. SFINAE is a very important and very necessary feature of the language. Remember, substitution failure is not an error. Instantiation failure is an error. To instantiate a class template, the template name should be followed by the template arguments enclosed in angle brackets. That results in a regular type. Each instantiation of a class template is a separate type. The compiler doesn't see any relationship between the different instantiations of the same class template and treats them the same as two unrelated non-template classes. So consider two unrelated class types. Even though their implementations and behaviors are identical, they are separate types. It is not possible to convert one into the other, or to implicitly convert a pointer to one into a pointer to the other. Instantiations of a template behave the same way. D of int and D of double are separate types. D of int can't be converted to D of double, and their pointer types are not implicitly convertible, just like the two unrelated classes A and B. Okay, but what about two very closely related types, such as int and const int? An int can be converted to a constant, and a pointer to int can be implicitly converted into a pointer to constant. Maybe the instantiations with these two closely related types are treated differently? Nope. D of int and D of constant are still separate types with no special ability to convert between them. As I mentioned earlier, the template argument kind must match the template parameter kind. Class template std array has two template parameters. One is a type and one is a size t. If our template arguments are a type and a compile time integral constant, everything is fine. If instead we supply types for both of the template arguments, the compiler will complain that it was expecting a constant and got a type. If we supply constants for both of the template arguments, the compiler complains that it got a constant 1 when it was expecting a type. Now for a more complicated template parameter kind matching example. Class template C has one template parameter, which must be a template that itself has one type template parameter. If we instantiate C with a type rather than a template, the compiler tells us exactly that we instantiated C with a type rather than a template. If we instantiate C with the template A, everything is fine because the template parameter and template argument match. We don't want any particular instantiation of A, so there are no template arguments provided to A. We want to pass the class template itself to C. Class template A will probably be instantiated within the definition of C, with whatever template argument C wants to instantiate A with. But we can't pass just any template as the template argument to C. It has to be a template with the correct signature. Class template B has a single non-type template parameter, but the template type parameter for class template C has to have a type template parameter. The compiler won't allow that and points out the mismatch. When using function templates, ignore the fact that they are function templates. Call them like regular functions without specifying any template arguments. Let the compiler deduce the template arguments. Once in a while, a function will be designed to require an explicit template argument. I'll cover that later in the talk. But normally, function templates are designed to be called without any explicit template arguments. If you have an explicit template arguments on a call to a function that doesn't document that, you are probably doing something wrong. As an example, here is one of the overloads of the standard algorithm transform reduce. There are 5 template parameters, but all of them are designed to be deduced from the types of the function arguments. And here is a call to that function from a talk that I delivered here 5 years ago. The only explicit template arguments are for the class template counting iterator. All 5 of the template arguments to transform reduce are correctly deduced. It would have been inconvenient to specify some of the template arguments, and it would have been impossible to specify the last one, since it is the type of a lambda, and those types do not have names. So don't specify template arguments when calling template functions. It's a really good idea to constrain your template arguments. That essentially means you list in the template declaration the requirements that you are placing on the template arguments. Some common requirements are that the type template arguments be copyable or default constructible, but it is possible to have almost any requirement for any kind of template argument. Constraining the template arguments in the template declaration allows them to be checked during substitution rather than during instantiation. As discussed earlier, that can help you avoid unexpected errors. Because constraining template arguments is such an important feature, C++ of course, has many different ways to do it. I will go through most of them very quickly. The best way to constrain templates is with concepts and requires clauses, which are C++ 20 features. But there are ways of constraining templates that work all the way back to C++ 98. Assume we have a function that counts the number of bits in an integer's representation that are set to 1. This function works for any integer type, but it only makes sense when the type of the argument is an integer. So how can we constrain the function so that substitution will only succeed for integral types? We can use an enable if check as part of the return type of the function. If the condition for the enable if is false, then the enable if type is not a valid type, and the substitution fails. You can also make the enable if check as the default value of a dummy template parameter. This has the same effect. You can put a C++ 20 requires clause after the template parameters, which checks the isIntegral type trait or the C++ 20 concept integral. You can also put the concept integral directly into the template parameter definition in place of the class or type name keyword. This constrains the template argument to types that satisfy the given concept. Since this is a function template and not a class template, it's also possible to put the requires clause at the end of the function declaration. And finally, the C++ 20 constrained auto parameter. This is a function template, even though the keyword template doesn't appear anywhere. If your compiler supports C++ 26 reflection that Herb Sutter discussed in his opening keynote, then you could also write your requires clause this way. But that's a topic for a whole nother talk, which I am not giving at this conference. To learn more about constraints, concepts, and requires clauses, go to Nico's talk about concepts at 2 o'clock this afternoon in this same room. If you want to be proficient at writing templates, then please learn how constraints work and use them in your code. The most basic principle for writing class templates is to keep it simple. Don't show off your template metaprogramming skills just for the sake of showing off. The next principle, which is a general coding guideline and not unique to templates, is to make it easy for users to use the code that you write. Sometimes fancy template metaprogramming can hide the complexity from your users and make your API easier to use. That's an okay reason to get fancy with your template. But please always keep your users in mind as you write template code. Document your requirements. especially the expectations that your template has for the template parameters. Do that in code using constraints like we just discussed when possible. Put the requirements in some other documentation if that isn't feasible. Member functions of class templates can have requirements that are in addition to the class's requirements. Because member functions are not instantiated until they are called, those requirements won't be checked until the member function is called. Generic programming is all about writing code that works correctly across a variety of types, and that's a good thing. But once in a while, that generic code doesn't work correctly for some of those types. We could make this the user's problem, telling them, use class do the thing with all your types, except for type foo, where you should use class do the foo thing instead. But that's not good. We should just make class do the thing behave correctly for type foo. That's where specialization comes to the rescue. We can define a class that will be used in the place of a particular instantiation. In certain conditions, the compiler will use the specialization rather than instantiating the class template. The specialization class can have a completely different interface than the main class template, but that's rarely a good idea, so please don't do that. An example should help here. The C++ size of operator only works for types that have a size. If you give it an incomplete type or a function type, that's a compilation error. Let's say we want a version of size of that can never fail. If the size of operator doesn't work for the given type, the operation should have the value 0 rather than being a compilation error. I don't know where this safe size of would be useful in the real world, but it's useful for demonstrating specializations. This is the generic implementation, which works for most types. Class template safe size of has one static context per data member named value, which is the size of the given type. Simple enough. But this doesn't implement the safe part of safe size of. If the template argument is void, the size of expression isn't valid and instantiation will fail. We can fix this with a specialization. We define a class that the compiler will use in place of safe size of a void. A specialization starts with a keyword template and an empty parameter list. The name of the class being defined is the instantiation that is being specialized. So here we indicate that we are specializing safe size of a void. Like the generic safe size of, the specialization has a static context per data member named value, but its value is 0 rather than the result value of size of. So these two declarations now correctly handle any type with a size and the type void. But there are other types for which size of is an error. To do that, we need partial specializations. A partial specialization looks similar to a full specialization, except that the template parameter list is not empty. The class definition is used for a set of instantiations rather than for just one instantiation. These are the generic template and the specialization for type void that we saw before. But now we add two partial specializations to cover the cases where the size of operator would be an error. The first partial specialization matches any type that is an array with unspecified bound. This partial specialization has its own template parameter, which matches the element type of the array. In this case, we don't need to know the element type within the class definition. The second partial specialization matches any function type because the size of operation errors out on function types. This may be hard to read because it uses a variadic template parameter and because the syntax of function types may be unfamiliar, but it works. So now we correctly handle void, unbounded arrays, and function types. That's good, but not complete. I can think of one case that isn't handled, and there are probably some others that I haven't thought of. But the fact that we are having to handle special cases one at a time and have no way to know when we are done should make us pause and rethink the design. It turns out that the correct way to implement safe size of is to flip things around. The generic case now handles all the problematic cases where size of doesn't work and we want the value to be 0. There is no way that we can forget some edge case. The partial specialization handles the usual case where size of is called. The pattern for using this partial specialization is in a requires clause. We want to use this specialization when size of has a meaningful value. But what if size of t is a compilation error? Sphene to the rescue. The requires clause is evaluated during substitution. If the requires clause fails, either because it evaluates to false or because it cannot be evaluated at all, then this partial specialization is ignored and the compiler falls back to the main template definition. So this does exactly what we want. If size of t is a valid expression, then value is size of t. Otherwise, value is 0. Going one step further, the real right way to do this is with a variable template that has a partial specialization. It is not necessary to have a class template with a const expr stata data member when a simpler variable template does exactly what we need. Not all templates can be specialized. Class templates and variable templates can be specialized, while type alias templates and concepts cannot. Function templates are more complicated, and I will cover that in the next section. At some point, you will run into a use case where you really want to specialize a type alias, but the language doesn't let you. Don't panic. There's an easy workaround for that. Just add an extra layer of indirection. Define a class template with a member type alias and define any specializations that are necessary. Then define a type alias that just forwards to the class. Voila, a type alias that behaves as if it has specializations. This pattern is common in the C++ standard library and especially in the header type traits, where this example was taken from. You may have noticed that some of the examples have the keyword type name in places where it doesn't seem to have any purpose. There was one example of that on the previous slide. The reason for this is that the C++ declaration syntax is messed up and difficult to parse. And sometimes the compiler needs some help knowing how to parse things. Here's an example of a very problematic statement. What does this statement do? If you think you know the answer, you are wrong. The statement can be parsed 3 completely different ways based on whether or not the names A, C, and D refer to types. If A is not a type name, then this is an expression statement that multiplies A with the return value of function B. If A is a type name, but either C or D is not a type name, then this is a variable definition. B is a variable of type pointer to A with an initial value of the result of calling function C. Essentially the same as the last line on this line at the bottom. If A, C, and D are all type names, then this is a function declaration. If that leaves you scratching your head, you are not alone. 30 years ago, when I was the C++ expert at my office, people would ask me to explain what the compiler was doing with declarations like this. This declares B to be a function that returns a pointer to A and has one unnamed parameter, which is a pointer to a function that returns type C and has one unnamed parameter of type D. It is identical to the declaration at the bottom, which spells things out a little more explicitly. Like I said, C++ declaration syntax is messed up. But what does this have to do with templates? In non-template code, the compiler can look up the names A, B, C, and D to see whether or not they are types and can then choose the correct parse for the statement. But within a template, it can't always do that. Consider this case where A, C, and D are names nested within a type template parameter. When doing the initial parse of the template, the compiler has no idea what A, C, and D refer to. In some instantiations, T::A could name a type, and in other instantiations, it could name a static data member. It depends on the value of the template argument T. But the compiler needs to know what it is during the initial parse of the function definition so it can know whether it is an expression statement, variable definition, or function declaration. That's where the type name keyword comes in. The rule is that type name must precede any qualified type name where the qualifier part of the name depends on a template parameter. If a qualified name that depends on a template parameter does not have type name in front of it, then the compiler will assume that it is not a type name. Consider this code snippet. As humans, we can guess from the names what this line of code means. The name value type, of course, names a type, and the names adder and object are probably not types. So this is obviously the definition of the variable p. But the compiler is not that smart. It doesn't know the meaning of the names of the various things. So it assumes that T::value type is not a type, and things don't go well. But at least the compiler is very clear about what went wrong. The compiler says that it assumed that T value type was a non-type, but when the template was instantiated, it turned out that T::value type really was a type. Even better, the compiler tells us how to fix the problem by inserting type name before the qualified name. If we follow the compiler's advice and insert type name in the right place, we're all good. Always write your function templates so that template parameters are deducible. Earlier I said that when calling a function template, you should let the compiler deduce the template arguments. This is the other half of that piece of advice. You should write your function template so that it is possible to call them without explicitly specifying the template arguments, except when you can't do that. One example of when it is not possible for a template argument to be deduced is when the template parameter appears only in the return type. The compiler can deduce the template arguments based only on the types of the function arguments, not on the return type. You will run into this situation when writing a function that behaves like a type conversion, as shown here. The template parameters are the source type and the destination type of the conversion. The source type can be deduced, but the destination type cannot. The function should be called like this, with the destination type specified explicitly and the source type deduced from the function arguments. The compiler is generally pretty good about deducing template arguments based on the types of the function arguments. But there is one pattern where the template argument cannot be deduced that you need to be aware of. The parent type of a function parameter cannot be deduced. It should be easy to convince you that the type T can't be deduced here. The compiler would have to look at every class type in the entire program to see if there was exactly one such type with a nested class or nested type alias that matched the type of arg. That is not feasible. The reason here is more subtle, but this is still a situation where the compiler cannot deduce the type T. In this particular case, a human can figure out that the template argument for T should be whatever the type of arg is. But that requires deductive reasoning, which the compiler won't do. There could be partial specializations and other complications that make it infeasible to deduce the template arguments of the parent class of a nested type. So the compiler won't even try. The next guideline, avoid complicated overload sets. Even without templates, overload sets can get quite complicated. When you throw template functions into the mix, the complexity can make it almost impossible for a human to write a function call that chooses the correct overload. To help keep things simple, all functions in the overload set should do essentially the same thing. The user really shouldn't care which overload is selected. If you have two functions with the same name that do very different things, you're probably doing something wrong. I will demonstrate this by giving you an example of what not to do. The standard container vector has lots of constructors. One of them takes the number of default constructed elements that the vector starts with. Another one takes an initializer list with the values of the initial elements. That seems like they are unrelated. But if we have a vector of an integral type, those two constructors can get in each other's way. It may be hard to see, but variable A is initialized with parentheses, while variable B is initialized with curly braces. You would think that A and B would be initialized the same way. But no, A chooses the first constructor and has 100 elements with the value 0. B chooses the initializer list constructor, so it has one element with the value 100. Calling with the constructor with two arguments doesn't help, because there is a constructor that takes both a count and an initial value. In this case, A has 100 elements with the value 200, while B has two elements with the values 100 and 200. If the element type of the vector is not an integral type, then we don't have this problem. The initializer list constructor isn't viable, so the count constructor is selected whether or not we use parentheses or curly braces. Don't write your overload sets like std vectors constructors. The user should know what a function call or constructor or overloaded operator does without having to know all the details of overload resolution. The behavior of a call shouldn't depend on the values of the template parameters. A constructor shouldn't behave differently for parentheses versus curly braces. The next piece of advice, be choosy about what your function template accepts. This means avoid writing function templates with common names that accept anything. This function here has no constraints on its template parameters, so it'll accept two arguments of any type. In this case, that's fine, because it has a unique name. Nobody is going to accidentally call a function named count stipples and report daces. But if you ever write this at namespace scope, you are in big trouble. This is an equality comparison operator that accepts two operands of any type. Since it is an exact match for any equality comparison, it will be chosen for comparisons that it wasn't intended, changing the behavior of its existing code and causing all sorts of problems. Don't do this. If a function template can be part of an overload set, then it must constrain its arguments to be exactly the types that it wants to handle, so that it doesn't steal function calls from an overload that will work better. Earlier when I was talking about specializations, I said I would talk about specialization of function templates later. Well, it's now later. The rules for specialization of function templates are more complicated, not a simple yes or a no. You're allowed to write a full specialization of a non-template member function template, but you can't specialize member function templates at all, and you can't write a partial specialization for any function template member or non-member. But ignore those rules. Don't bother with them. The guideline that you should follow is simple. Don't specialize function templates. If you find yourself wanting to create a full specialization, just create a non-template overload of the function. If you find yourself wanting to create a partial specialization, just create a template overload of the function. Let's say we have a do something function that takes a single argument that satisfies some condition. And we find that we want it to behave a little bit differently for C-style strings, because C-style strings have their own idiosyncrasies and aren't normal C++ objects. Rather than specializing the function, we just add a non-template overload taking a const char star. The C++ overload resolutions will do the right thing. We have a function process collection that takes as its argument anything that looks like a container. Let's say we want to process std list containers differently, because they have different complexity guarantees and support somewhat different operations. Rather than specializing process collection, we just create an overload of process collection that takes a stood list with any element type. Again, the magic of C++ overload resolution will do the right thing and call the correct process collection overload. My apologies for the fire hose of information. I hope you were able to successfully drink at least a little bit of the content. Once you feel like you understand the topics in this presentation, I highly recommend that you watch Walter Brown's two-part presentation, Modern Template Metaprogramming, a Compendium, from CppCon 10 years ago. He did a fine job of explaining how templates work at a level or two above what I tried to cover in this Back to Basics presentation. I can't really summarize all the syntax for templates and all the language rules that apply to templates. That's a lot of detail that you will have to learn over time through practice and experience. But I would like to review some of the higher level concepts and practical advice that may have been missed in the fire hose of data. Define templates and header files. Know the difference between substitution and instantiation and when each of those happens. Substitution checks that the template arguments correctly match the template parameters, and it checks that the declaration of the template, such as checking the function's signature. Instantiation happens after substitution and checks the entire definition, such as the class definition or the function body. Substitution failure is not an error, or sphene. When a failure happens during substitution, the entity is ignored. The substitution failure by itself is not a compilation error. When writing a function template, try to make all of your template parameters deducible. When calling a function template, don't specify the template arguments. Let the compiler deduce them. Constrain your template parameters so that your template accepts only the things that it was designed to handle. And finally, keep it simple. Simple means as simple as is practical for the given situation, not simple on an absolute scale. Keep it simple applies to everything. The interface of the code that you write should be simple to use correctly. Your implementation should be kept simple so that it is easier to maintain in the future. And keep your overload sets simple because a complicated overload set can be a nightmare to use and to debug. Generic programming in general, and C++ templates in particular, can be challenging to learn and to master because it requires new ways of thinking about code and of understanding how code is processed by the compiler. This will take time. Don't be discouraged if you don't get it right away. Keep at it until it clicks. Templates are an integral part of C++ these days. Even if you never have to write a template, you'll be using them constantly, so you will need to understand how they work to be a proficient C++ programmer. Thank you for coming, and good luck.